Hi everyone, we're going to begin our discussion of rotational kinematics with a discussion about angular displacement and radiance. Before I get too much further into this, the words rotational and angular are sort of synonyms. It's like calling something a Kleenex or calling it a tissue. It's the same thing. It's just sort of two words used to describe the same thing. So they are interchangeable. When we talk about angular displacement and radians, we're talking about how far something actually moves in a circle, how far something actually is displaced. Now, every time we start with one of these rotational ideas, we're going to begin with the linear version, and then we're going to translate that into rotational because you have experience with the linear, and so hopefully for me, this makes it easier. When we discuss linear displacement, we use the symbol x and we use the units meters, and we describe how far an object would move in a straight line. Now that we're talking about angular displacement, we are talking about how far something rotates. So if an object is here and it rotates through an angle theta, that is how far an object is rotating. Now that might be a fan blade, a gear, a carousel, anything that is going to have circular motion. So the symbol we use for rotational displacement is the same symbol we have used in the past for angles, the Greek letter theta, but the unit is the radian, and we'll talk about radians a little more in the next slide. This is a measurement of how far something is actually rotated around its center. Now, radians are the unit of angular displacement that you must use when you are talking about and using the rotational kinematics equations. In one circle, there are 2 pi radians, and 2 pi radians equal 360 degrees equals 1 revolution. This is definitely something you want to write down, put a box around, make sure you've got that handy because we're going to use that in a minute. When we are measuring angles with radians, we always start on the x-axis and we move in the counterclockwise direction. This is the same way and direction that is moved in math, different than the direction things are moved in a compass rose, going from north to south to east, etc. If you start at the x-axis and move up to 90 degrees, you go through pi half radians. If you go all the way over to 180 degrees, you have pi radians. If you go all the way over to 270 degrees, you have 3/2 pi radians. Or if you've gone all the way around 360 degrees, you have 2 pi radians. And we're always going to use radians when we're calculating using angular displacement. Now let's start by converting some other units into and out of radians. And here is the conversion factor we're going to use. You can leave your calculator in degree mode. Okay, you do not have to change your calculator to radian mode unless that's something that you are very comfortable with and very familiar with, but you don't have to change into radian mode. I'm going to show you an easy process where you can determine angles, revolutions, and radians, and we're going to convert the way we've converted everything else so far. So let's say I've got 37 degrees and I want to know how many radians that is. I am going to set up a TIE fighter. And if I set up my TIE fighter, I want to get rid of degrees and keep radians. Well, here's my conversion factor. And so if I want to get rid of degrees, I have 360 degrees on the bottom. That equals 2 pi radians on the top. So I take 37 times 2 times pi equals divided by 360. And when I do that, I end up with 0.65 radians. Now, I'd like to have you try these two, and you're just going to set them up the same way. Take a TIE fighter and convert these. So hit pause, and I'll come back in a moment and give you the answers. All right, so 1.37 radians. We're going to get rid of radians, go to degrees, 360 degrees, 2 pi radians. When I did that, I got 78.5 5 degrees. 0.4 revolutions, because often things are given in revolutions. Each one revolution is equal to 2 pi radians. When I do that, I got 2.51 radians. All right? That's not too bad. We will come back later and continue with rotational kinematics.